All right. So last time we were talking about integrated rate laws, correct? Okay. And we decided to look at the more difficult one first. That guy, right? Okay. This type of reaction, what type of reaction was it? Yeah, bimolecular, we had A plus B go into some product. We didn't really care about the products because we only care, this is a reaction that's going in the forward. It's not at equilibrium. There's no other crazy things to encounter. We got to a point where we were defining things. We defined the concentration of A as A naught minus whatever reacts. And we did the same thing for B, right? Okay. And what were those knots again? Yep, the initial concentration. And we wiggled our way all the way to the point of doing an integral that got us the following result. Oops. What did we do? We had K. Did we say K sub R, or did we just say K?
Yeah.
Ah, okay, my bad. Did we do that integration, or did we just say this was a definition that we had? We hadn't done the integration yet.
We got to that part.
We got to this?
Yeah.
It had ones in the numerators.
Oh, it's ln 1 over A minus X. Yeah.
Ln of 1 over A minus X. Oh, okay. So like we had an indefinite integral that we pulled from the table and we integrated, and we had like little b's and little a's, right? Okay. If you sub in for those little a's and little b's, this is what you should get overall. Yeah, that's a good question. Let me stare at that for a second. Because I think I wrote the indefinite integral wrong. Minus X, right? That's what we had in there. Okay. Where the hell were we? Okay, so we hadn't like developed an integration yet. Okay, one step back. Okay, so what we said was is we had, like we were looking at this thing, right? Oh, excuse me. We could express it like this. That's where we were? We didn't do an integration?
No, just do
Yeah, I'd like to stare at what the hell I'm doing here. Okay, we got blah, 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 blah. Okay, yeah, I wrote the indefinite integral wrong. Like when we integrate this thing.
Yeah.
Yeah, I wrote that wrong. I'm sorry. There should be an A naught. Or A and B up here. My bad. Okay, so we're to the point where we've integrated everything. Right? Or at least we're okay there. Just know that this comes out of the integral and we get t. Okay. Are we okay with this? So we integrated our expression, and this is what we arrived at. Or you will arrive at. This looks complicated, though, because we have these x's, and those are things that are being consumed, right? What else are these two bits here? What else are they equal to? Yeah, they're A and B. So at some other time, if we kept track of the production of A or what the concentration of A was at some other time, or B at some other time, you'd get this, right? Okay, what can we do with this stuff? Yep, smush it all together. And we're going to move these knots over to the other side because what are those knots? Are they changing? No, not really. They're a constant. So we could smash everything together. Or what, Lily, you said stack. Yeah, stack. We could do, let's do A naught divided by A. And we're going to move that other thing over. Ah. As far as I want to go with this thing. Yeah. Okay. This is a little more difficult to keep track of things, right? We could fit this to a line, but it's going to be difficult because we would need to know the concentration of A, and we would also need to know the concentration of B, or the ratio between the two. We could set it up and we could still solve. Okay. The amount of work that we had to do to get to that point is way more difficult than if we had a single reactant. Let's investigate what the integrated rate law would look for that guy. Are there any questions about that one? Sorry, I gave you the wrong stuff here. Okay, another second order reaction. Oops. We could look at it in terms of rate is equal to squared like that, right? For a rate law. Let's figure out what our integrated rate law would be. What's another way we could define the rate? Yep. And what sign do we need since it's a reactant? Yeah, negative sign would be equal to K A squared. Okay, we got to shuffle some stuff around. What do we want on one side? What do we want on the other side? Yep, we want the A stuff together, and we want to isolate the dt by itself, so it makes it easier to integrate. So what we get, can we integrate now? What are we going to integrate to on the side with A? Yep. A naught to A at some other time. Have we been using a sub t here? Okay, let's put a sub t there. What about for the other integration? Yeah. When we integrate this side, what are we going to get? Yeah. And we do AT minus, I know this seems kind of foolish, but we're going to keep. And what's it going to be equal to? Yeah. Okay. We're going to distribute that negative sign through. So that goes away. And we get this. Okay, we want this to look like a linear line. Excuse me. Single variable line. What would you do to shuffle things around? Yep. You got KT plus okay, this thing's a bit easier to plot than this guy. What's my y? What's my x? What's my slope? Yep, slope is k. Yep. This thing, b, and then, yeah. So now, if you wanted to compare if it was first order versus second order, first order, what would you plot? Look back at your notes. Yep. And what about second order? Yeah. And you'd compare those two, and which one would you go with? Yeah, whichever one's the most linear. How do you determine which one's the most linear? You do statistical test. R squared is what we used in Gen Chem. You can use R squared, but you should really also do additional statistical tests to say, hey, are they actually different?